Good afternoon, everyone. I'm Judy Geller, Director of MetalCon, and I am delighted to welcome you today to MetalCon Live. Today, Kevin Cox from ATAS International is here to present Interior Acoustics and Sound Control using Metal Panels. Before I hand you off to Kevin, I want to make you aware of a very special edition of MetalCon Live that will be taking place here on June 22nd at 1 o'clock Eastern Standard Time. We are launching a really important series to help young professionals, rising stars, and in short, the next generation of leaders in the metal construction industry, as well as their managers, to prepare them to step up and take their careers to the next level. The first session, called Personal Branding, an Important Skill for Professional Success, will be presented by the highly popular Dr. Melissa Furman. She's really a game-changing presenter. She's going to present this engaging 60-minute virtual presentation, and you're not going to want to miss it. Then the conversation will continue at MetalCon 2022 in Indianapolis next October 12th through the 14th. We'll have an exclusive education program called From Employee to Manager, Transitioning to a Management Role, and she will be managing that as well. Following that session at MetalCon, there will be a happy hour to get to know each other, do some networking, and just have a good time. And we're happy that our friends at Sabine are going to be sponsoring that happy hour. So spread the word and plan to attend, and please encourage your rising stars to join us on June 22nd for the next MetalCon Live, and come to MetalCon as well. By the way, this is also the perfect time to tell you that MetalCon registration is open with 200 plus exhibitors, 25 learning sessions, pre-show workshops, new networking opportunities, and Joseph Newgarden, a winning Indy 500 racer, keynoting. It is really going to be an exciting show. And architects, we have a lot of special things in store for you as well this year. We're bringing the Architects Experience to Indy for its second year. Program details are coming soon, and it's going to be a good one. Finally, if you need technical help during the webinar, please reach out to MetalCon support in the chat box. And don't forget to complete the post-webinar survey to earn your AIA LUs for today's session. That's it from me today. And now I'm going to hand things over to Kevin.
Thank you, Judy. I appreciate everyone having us today. I want to be able to show that everyone can see our screen and our presentation today for interior acoustics and sound control using metal panels.
Go ahead and try resharing that for me, Kevin.
All right. We will go there and there. All right, how do I make my thing bigger so I can share screen?
So down at the bottom of your screen, in the up in the upper right-hand corner, you should be able to see three little dots.
Make it bigger. I got to share screen.
There you go.
See, all you have to do is speak, and then magically we are sharing our screen again.
Perfect. We see it. Awesome.
All right, fantastic. All right, guys, once again, sorry about the delay. Our presentation today is on interior acoustics and sound control utilizing metal panels. I am with ATAS International, which stands for Aluminum Trim and Shapes. We were founded back in '63 by Jack Buss, and it's still family run. We have manufacturing in Allentown, PA, Mesa, Arizona, University Park, Illinois, as well as coil coating in New Jersey and post painting in Trenton. So pretty much 60 years of experience, but still with a family feel. Number of things we all work in. We do metal wall panels, perforated metal sconces, closures, equipment screens, metal roofing. I joined the company about 6 years ago and looked at some of the things and really looked like we could expand that. Curved custom fabrications. We have a specialist, Mr. R.C. Anto, who runs our insulated metal wall panel division. Kevin Cox, that's me. I run the interior ceiling and soffits. We're moving from Division 7 to Division 9. And then we have an expert on staff, Mr. Bob Leclerc, who has actually written code for perimeter edge metal. So anything we can help you with, we always like to get involved. But with no further ado, we will start our interior acoustics and sound control using metal panels. This is accredited by the AIA. If anyone does need a certificate, please reach out to Judy or myself, and we can get those to you for accreditation. It is copyrighted, so no reuse or rebroadcast without the express written consent. I don't know if that has to be expressed and written, but if you get in touch with me, we're happy to share slides, bits and pieces, or any part of the presentation that you may need for your day. So our learning objectives for today, we're going to define sound. We're going to look at the physical properties, actual sound waves, and identify how it travels and interacts within a given space. We're going to take a brief architectural acoustics history lesson. We're going to look at Wallace Sabine's formula to convert Sabines to meet a specific area's needs to tune a room or for sound control. We're going to look at noise reduction coefficient, ceiling attenuation class, and sound transmission class. And last but not least, we're going to look at the ABCs and demonstrate placement in alternative spaces to provide acoustical treatment within a given space. So wood today, or metals today, have come a very, very long way, as we all know. This is actually a faux wood ceiling at Moser Elementary School out in Connecticut. It's actually a magnet school, and they wanted to carry these inside and out. And of course, metal with a wood finish was the perfect answer. Let's look at the characteristics of sound. What makes up sound? And start by doing a definition. So the acoustic or acoustics has a lot of connotations in a lot of meanings. That first one, a musical instrument without amplification, typically guitar, fun around the campfire, but really not for our purposes today, the definition we're trying to drill down on. Now, the branch of physics that's concerned with the properties of sound, that gets us a little closer. But for today's purposes, it's really the properties or qualities of a room or building that determine how sound is transmitted in it. So sound or a sound incident is just that. It's a disturbance or turbulence that passes through a medium in the form of longitudinal waves from a source to a receiver, causing the sensation of hearing. Now, this medium doesn't have to be the atmosphere or sound like we hear currently, sound waves coming through your speakers and through the air into your waves. It can be a fluid, a gas. We know that sound waves travel more rapidly underwater, hence sonar. This is going to age me, but when I was a kid, we had these wooden sticks. They were about 3 foot long. We called them a yardstick, and you could put one end of it in your ear and tap on it, and you would hear that sound within the wood before you would hear it any other place. And the reason that is because speed travels more rapidly, the more denser the molecular composition of what the medium it's traveling through. So like we said, it's an energy of alternating high and low pressures that move out in a longitudinal propagational direction. And these different air pressures create the different sounds that we hear. So what you see on the bottom is a wavelength. That's basically a representation of a sound wave. The distance between 2 peaks and 2 valleys is the actual wave. And we measure one peak to peak or valley to valley in seconds with the letter T. Now, the frequency is the number of oscillations per second, and that's measured in hertz, RHZ. And then the amplitude is the distance between a crest, the highest point, and a valley, the lowest point, and that's measured in decibels or dB. So when we have a lower amplitude, we have a quieter sound. When we have a higher amplitude, we have a louder sound. When we have fewer oscillations, we have a lower pitch. This one's a little tougher. And when we have higher oscillations, we have a higher pitch, and all the things in between that make up all the sounds that we can hear. Now we have the sound wave, and we introduce it into a space or into a room, and we know that these sound waves are going to be interrupted by objects, peoples, furniture, the boundaries of the space itself. All these things will impact or interrupt these sound waves. And all these materials are going to be varying degrees of 2 types: those that allow sound to pass through, and those that don't, and then kind of that gray area in between. Now, once encountering a barrier, sound waves are likely to behave in the following ways: absorption, transmission, refraction, reflection, diffusion, and diffraction. So absorption. Well, absorption is basically when the sound hits an obstacle. Some of that energy is reflected back, as you can see, but some of it is lost molecularly or transferred into the barrier itself. That lost energy is said to be absorbed. Now, the sound wave itself, thickness, porosity, hardness of a material, are all going to affect the amount of absorption of that obstruction. Transmission. This occurs when a sound wave is carried through an obstacle, through vibration, and re-emitted on the other side. So we know that some of it's absorbed, but anything we can hear on the other side, in this case, it looks like a partition, we say is transmitted through that obstruction. Now, these can be airborne, structure-borne, impact-borne, but anytime you can hear a sound move from one side to the other, that's considered a transmitted sound. Now, refraction is a variation of transmission. That's the bending of a sound wave, kind of the turning either up or down, depending on the angle and the sound incident itself, and the different compositions within that obstruction. In room acoustics, we really don't have a lot of ways of controlling or preventing this, but it is a phenomenon that happens, so we did want to include it in our presentation today. Reflection. This occurs when the wavelength of the sound, the molecule, is smaller than the obstruction it's hitting. Sound waves hit every side of a room and start to bounce back until the decibel level is reduced to 0, or the sound energy is reduced to 0. Now, diffusion, we know that usually when a sound wave hits, whatever that angle it's hitting a flat obstruction at, it's going to be about a mirror image between its primary ray and its secondary ray. However, there's a splaying of those rays, especially off a flat surface, and that splaying is a diffusion. We call that diffusion, and this is another way that sound energy dissipates itself to 0. And last but not least is diffraction. Very much like uplifts or eddies, when sound waves move around a 90-degree angle, they don't necessarily have to strike the surface, but moving around that 90-degree angle, they also splay or open up, and we call that diffraction. We can control this to some degree by bullnosing corners, not having a lot of right angles, especially outside right angles. But more often than not, we want this splaying or diffracting, because once again, this is another way we lose sound energy within a space. This is an interior of Mesa, Arizona. The architect was trying to get that desert Southwest feel by creating a snakeskin and carrying some of those colors throughout the interior. Once again, these are all metal panels with the exception of the stone on the front fascia and on the floor. Another unique use of metal within interiors today. So as promised, we're going to have a brief history of architectural acoustics. The credit to modern day architectural acoustics is really given to the Greeks and Romans. But they were really trying to solve line of sight problems with steeply banked semicircle configurations. A lot of these ancient auditoriums, you can see the gentleman standing in the middle, where you could speak at a regular decibel level and be heard throughout the space. But once again, what they were looking at is solving line of sight problems. But visual waves and audio waves traveling along the same interstates, by solving line of sight, they wound up with very proficient acoustics. Later on, the Romans built large slanting roofs that were shading devices. And once again, by mistake, they pushed waves back out into the auditorium, into the farther spaces, creating some of the first reflectors. There really isn't any reference of architectural acoustics until the 1st century BC by Vertivius in a book called The Architecture, where he describes Escher. What Escher, very much like the acoustic guitar that has a resonance chamber, where these large vases were placed around the outsides of auditoriums, and that resonance chamber would give some reverberation, some richness of sound, because there was no reverberation. These sounds were just single pass and moving out. The Middle Ages only have an elementary knowledge of acoustics, and really architectural acoustics goes out the window, as churches are characterized by overwhelming excessive reverberation, very hard surfaces, very large spaces. And we don't really hear anything about acoustical or architectural acoustics until the turn of the century. Well, at the turn of the century, in walks the handsome gentleman to your left, Mr. Wallace Clement Sabine. And Sabine actually used seat cushions and pipe organs as sound sources in a Harvard laboratory to drill down and measure the properties of sound. Later, he goes on to be the acoustician of record for the Boston Symphony Hall in 1900. Still considered to be one of the best acoustically proficient concert halls in the world, even to this day. That's that sketch you see in the center. But really, his gift to architectural acoustics was he came up with a reverberation time formula. It didn't appear into print until about 3 years after his death, but that formula is still used pretty much in its original form to this very day by acousticians all over the world. So Sabine was able to determine through the experiment with these cushions and these pipe organs, a definitive relationship between the quality of acoustics, the size or volume of a chamber, the amount of absorption, with the most important factor being reverberation time. Now we know from previous slides that sound produced in a space will bounce off and reflect, gradually losing energy. As these sounds collide with each other, the phenomena is known as reverberation. Now, too much reverberation is going to have a negative impact on speech intelligibility, and too little will reduce the warm, rich sounds that we normally hear, like in an orchestra call or like in the Boston Symphony Hall Orchestra. So Sabine's formula was RT60, or reverberation time 60 dB. And basically what it's measuring is a 60 decibel drop in a sound incidence decrease, and what that time is in seconds. So in this example, it's 100 to 40. It doesn't have to be 100 to 40. It could be 120 to 60. It could be 90 to 10, but it's or 90 to 30, excuse me. My math's a little off. But it's basically the time it takes for a 60 decibel decay to occur, and that time in seconds. That rate of decay is going to depend on the amount of sound absorption, the sound incident, the room geometry, and the obstacles that are in that room. So it looks a little daunting, but it really isn't. RT60 that's basically going to be in a seconds, is going to equal that 0.049, which is the speed of sound in feet, times the volume of the room, which is length times width times height, times that absorption coefficient. That absorption, that A, is the surface of each wall, ceilings and walls and floors, and they put an absorptive coefficient or average on there that they times it by. Hard surfaces is usually 1. They divide that by the speed of sound times the volume of the room, and that should model roughly in seconds what your RT60 is going to be. Now, different building materials will have varying amounts of acoustical absorption. If we're treating a space, the higher the absorption, the less footage will be needed. But because of the algebraic relationship, we can remove one variable. So when we looked at that model before, we were trying to model a room's RT60, what it was going to be in seconds. But if we know the RT60 that we want to get to, and we know the volume of the space and the size of the walls, we can figure out that absorption coefficient, or how much absorption is going to be needed to treat that space in Sabine's. Now, generally speaking, for general purpose, a 1.5 to a 2.5 second RT60 is about what we're looking for. Larger auditoriums, it's going to be a little higher than that. Smaller spaces are education spaces, libraries, medical, probably a little less. When I worked in another lifetime for USG, they had an anechoic testing chamber, had all these foam kind of things coming off the walls, and you would go in there to test a sample, and it was almost like you were holding a shell to your ear, because you could hear like the blood rushing in your head. It became uncomfortable. It was so devoid of sound, or so acoustically dead. The other side of that is when you get that 3.5 seconds, you get a lot of echoic effect, a lot of reverberation. You get to 5.5 seconds, you really start to lose speech intelligibility. There's kind of a bit of a communication breakdown because it's so echoic, and so forth and so on. Well, God bless the internet. This is public domain, so anyone can use one of these, but there's a lot of reverberation calculations or calculators you can use. You can see the width times height times length to get that volume in feet or meters. Your walls, floor and ceiling, what those spaces are, and then a number of hertz that you can test across, and this will give you a modeled RT60. It's kind of an acoustician in a jar, or you can work it backwards if you want to see how much treatment a room needs. And once again, these are the hertz across the room. The voice hertz are that 125 to 250 range, if that's what you're working with. But these are all over the place. And like I said, they are public domain. So you're not doing any copyright infringement by using them if you wanted to model spaces. So we looked at these spaces and how they react. And now let's look at materials. More specifically, noise reduction coefficient, sound transmission class, and ceiling attenuation class. And we're going to take those in order. First is noise reduction coefficient. Anyone that's opened up an acoustical ceiling catalog or acoustical wall panel catalog has definitely seen NRC, or noise reduction coefficient. And what that is a scalar representation of the amount of sound energy absorbed as soon as the sound incident strikes a surface. It's represented by a decimal or percentage, and it's rounded to the nearest 0.05. So an NRC of 0 would indicate a perfect reflector or perfect reflection. An NRC of 1 would represent perfect absorption, or 100% of that sound energy upon first pass is being absorbed. If we had something with an NRC of 0.50, that would mean that 50% or half the sound energy is being absorbed upon first pass. This is averaged across 4 hertz, 250, 500, 1000, and 2000. And once again, it's rounded to the nearest 0.05. We do have a sound absorption average in that anechoic chamber. They were drilling down to get a more exact reading, and it was an SAA. It's very similar to an NRC, except for it's a wider band of hertz. It starts at 200 and goes to 2500. And instead of being rounded to the nearest 0.01, it's rounded to the nearest 0.05. So here's kind of building materials and what their absorptions are. As you see, acoustic ceiling tile is not that's going to be your most absorptive. We'll talk about that later, but carpet with pad. Today's carpet with pad's more loop pile. It's probably a 0.30. If you're getting up to that 4050, that's going to be something in a nice shag, which I don't think we're using too much anymore, but it is possible to get that. But the point here is that most building materials really aren't that absorptive. So next is sound transmission class. So we know about transmission of sound passing through an obstruction, and what STC measures is the reduction of decibel from one side of an obstruction to the other. Now the word deci is meaning base 10. So 10 dB up or down is a physical and literal halving or doubling of the sound wave itself. And then the last part is by its inventor, Alexander Graham Bell. And, Bell was actually involved so much in sound because he was going deaf, and that's why he wound up with the telephone and the phonograph, and you guessed it, the decibel. So STC can be between partitions, floors, walls, inside to outside. But basically, if you have a sound incident that's an 80 decibel on one side, and you can measure 40 decibels on the other, then the STC of that would be a 40. It is literally that simple. Now it's a lot tighter measurement. I'm not going to read all these to you, but you can kind of see the 25s, 30s sound is passing through relatively easy. Most commercial partitions are going to be in that 40 to 50 range. As you get higher and higher, it becomes more cost prohibitive and a little trickier to get something that's close to soundproof, but it's not impossible. But those ranges run roughly from a 25 where sound is passing through pretty readily to 75 and 80 where you're getting something that is almost soundproof. And that's sound transmission class. Last but not least, the ceiling attenuation class. It's essentially STC, and this came to us from the Acoustical Ceiling Manufacturers Association, CISCA and Wiki and some of those. But it's basically the same measurement. It's the decibel drop, but it's a 2-pass test. With the advent of walls not going to ceilings, going grid to floor instead of slab to slab and open offices, there was a loss of privacy. So what this is a measurement is the decibel level on one side, going up, hitting whatever that structure is above, and being measured in its adjacent surface. And once again, if you have a 60 decibel incident on one side and you measure a 20 on the other side, then you're going to have a ceiling attenuation class of 40. And that would be very, very high performing. So this is also a very tight measurement like STC, where 25 is low and a 35 is high. The one thing we want to know that if we are specifying a higher CAC ceiling, we want to make sure that their wall specification is going to be at least 40 plus. You don't want to spend money in the ceiling piece if you're going to lose that sound privacy through the walls. And then there's a quick kind of guy on the side, you're showing the CAC going up and over, the STC passing through the wall, and then the NRC being absorbed up and down into the ceiling. We looked at sound control and its components, what makes it up, how it interacts within a given room, and how to use Sabine's equation to literally tune a room for a given purpose. Now we're going to look at the ABCs and kind of how to place these high NRC materials and spaces, as well as unique, resilient hard surfaces that are also acoustically proficient. So I mentioned earlier acoustic ceiling tile. Acoustic ceiling tile has really been the go-to for, decades. Very, very easy, very, very convenient. It's actually made from a byproduct of slag. The tiles themselves are mineral fiber. So they'll take the slag and spin it like glass, like fiberglass, into these long fibers, press that into a mat, paint it with an acoustically transparent paint, and then perforate it and fissure it so there's places for the sound to go to, for it to get caught in. And it's very, very simple to install. It creates this nice plane and interstitial space for all the MEP trades to be accessed and yet hidden out of sight, usually 2x2, 2x4. And if you have a space where, you know, your ceiling height is 8-9 feet, just treating one plane with acoustical ceiling tile is usually enough to control reverberation. Now, if we want to get a little bit more flexibility, we can work with geometry, with shapes, with textures, with colors. Floating clouds or fabric wrapped sound panels. The nice thing about sound panels, these are usually chemically hard edges. They're, you know, wrapped on one side, the visual side, but they're absorptive on both sides. So what that means is that you can use less panels and still get a 2-pass effect. Unlike the decibel or the ceiling attenuation class where you're measuring the decibel, we're actually getting absorbed in the top. So you get that first pass coming up. Then anything that goes off of structure and bounces down, you can count on getting caught on a second pass or the backside. So what that means from the design perspective is that we can use less material and still get the same amount of absorption because we're getting that 2-pass effect. If we have even larger volumes and need more space, we can turn these on their side, usually a Z-clip or some type of mechanical attachment. Can be very eye-striking, like on the right, that little dot matrix, kind of picking up school colors or branding colors there in the center, where these can fade back into the design and be more muted colors and just acoustical units, like we see there on the left, which looks like to be a lecture hall. We have even bigger volumes and need even more treatment. Well, baffles and banners. So here we can really maximize high ceilings, get some absorption within them. Once again, you can see in the center, that's more school colors or branding colors and a focal point where each side is more to be more muted colors and made to kind of fall back into the design. One of the rules of thumb with baffles or banners is however deep they are, however long they are, wherever that drop is generally what we want to space them at. So if you have a top banner and it is closer than the drop, you're really not going to be utilizing the top part of that absorption. If we spread them out and get them farther, then we're not utilizing the square footage within the space. So we're circling back around. So acoustical ceiling tile in its basic form, this fissured and perforated pattern is pretty cost effective. But once you move away from that, that standard perforation, if you want to get a larger monolithic or smooth surface, prices double or triple. So your upfront cost goes up exponentially. They can stain, break, fade over time. Generally speaking, the mineral fiber versions have a maximum range of 70 to 80 NRC. To get higher than that, you'd have to go to spun fiberglass. So, what if there was a more resilient panel and finish that was available with even a higher NRC? Well, I know this is going to come as a shock to everybody, but the metal guy is touting perforated metal acoustical panels. It does seem a little counterintuitive because a solid metal panel will reflect sound. However, a perforated or micro perforated panel allows sound to transfer through. Now, once we transfer through, we need to catch it on the other side. But by doing so, we can create a very, very resilient surface with some very, very astute or high, almost perfect NRC. And here's a residential hall where they used actually a metal standing seam shingle would be a roof, but as a wall application. And then faux wood, basically these are mechanically attached, almost soffit panels, but exterior metals coming inside and really sparking a design or an impact. So like I mentioned, the ABCs of acoustics. So when I say ABCs, what exactly am I talking about? Well, with metal, there's absorption, there's blocking, and there's covering. So like I mentioned, we can perforate metal panels and allow sound to transfer through, but then we need to catch it with something. One of the ways that we can do that is with acoustical fleece or sound text. In a lot of these, when I do these architecturally, they don't want you to mention product names. The thing is, the only people that really make an effective acoustical fleece is Freudenberg, and it's called sound text. It's very much like Kleenex or Coke. The product name has become synonymous with the actual product because or the acoustical fleece piece, because it's used interchangeably, because they're really the only one that it is. And what it is a very thin material. It's almost like a felt. There is an acoustically transparent mastic on it that is heated, and that felt is adhered to the back of a perforated panel. In this case, it looks like a ceiling tile, but just about any panel, as long as you have 18 to 22% open, you're going to get an NRC of somewhere between 70 and 75. So about 3/4 of that sound energy is going to be absorbed. Now, that's not perfect absorption, but you're not giving up any of that interstitial space by using an acoustical fleece. It doesn't particulate. You don't have to worry if you're ever going to turn any of these sideways about it calling out, because it is adhered to the panel. I mean, you're getting some very, very good acoustical performance without, once again, utilizing or losing any space that you're utilizing for, duct work, for communication, for electrical, and so on. Tested with this is a product I like a lot. This is CFAB, or cellulose fiber acoustical bat. It is highly recycled and highly recyclable, in a 2x2 or 2x4 or 4x8 kind of semi-rigid. And what it is, it's actually recycled denim and polyester. So it seems like it's a flashback from the 70s, but they treat it in such a way that it passes NFPA 285. So it's suitable Class A for all commercial building. If you get a 2-inch, you're pretty well insured to get an 8.5 to 0.85 to a 1.0 NRC, depending on how much perforation you have on the metal face. And also, it's not an irritant. So when people are installing these, using these, touching these, you can touch your face. You can. It's not an irritant like fiberglass. You don't get all itchy and sweaty or break out in hives by utilizing this. And it's also a very, very green product and very, very planet friendly. So that's CFAB. The most common, our good friend fiberglass, usually a very bright color, yellow or pink, depending on the manufacturer. So we have to encapsulate it or put some type of scrum or felt or black fascia in front of it so you don't see the color through the perforations. Most commonly, it's a 1.5 to 2-inch density. You can still get a pretty high NRC, 8.5 to 1.0, but it is an irritant. And it does not recycle well. And once it gets wet or collects humidity, it loses its acoustical performance. However, it's extremely cost effective. So it is widely used throughout the industry for acoustic backing to get that A or absorption. If you've ever had anybody that has a champagne taste and a beer budget, another way to get down or drill down on something where you can get acoustical performance is by the use of acoustical duct liner. Now, this is still basically fiberglass, but pressed. However, because they don't call it an acoustical bat and they use it in large duct trunks to reduce wind velocity, it's very, very cost effective. It comes in basically 100-foot or 50-foot rolls. They're the same size. It just depends whether you're rolling out 1-inch or 2-inch. It is generally a 1.5 density per cubic square foot, and it already has that black facing on it. So once again, you're not going to be able to see it looking through the perforations when we're looking up or down on an assembly or through it on a wall assembly. So anything you can do with a mineral fiber panel, we can do with aluminum. The reason I say aluminum, certainly we can do it with steel, but perforating aluminum, it doesn't rust, it doesn't corrode. We don't have any issues with that. And also aluminum, as far as being planet friendly, is one of the most green materials we have. This is true because it's more cost effective to actually recycle aluminum than to go out and try to get iron ore to mine virgin material. So mineral fiber, although it's made from a recycled material, at the end of the day, they really don't have a good way. They grind some of it up and try to reintroduce it into some of the slurries, but it doesn't really take. More often than not, the reality is that when this mineral fiber is done, it's going to wind up in a landfill. It's expensive to try to recycle it, and the processes aren't quite there yet. However, when we're looking at metal or aluminum, it's more cost effective. So that aluminum has a value. The idea that someone's going to go in there, pull it down, and recycle it is a very high probability because it's more profitable to do so. So it's one of the few places that capitalism actually drives a little bit of green building, which is kind of a nice effect for it. But once again, any of the bolt slots, the reveal edges, the square edges, narrow line, just simple lay-in, anything you can do with a mineral fiber panel, we can do with a aluminum panel perforated, and we're going to get a higher performance out of it. You guessed it, we can also do the islands. These are usually going to be trimmed off or turned up edges somehow. We can do different types of infills, different types of fillers, and you're also going to get that same two-part pass. So if we turn a large metal panel like you see on the left, micro perforate it, put an acoustical 1.5 density batten there, you're going to have a perfect absorption, both going up and down. Once again, that means less treatment of the space, a whole lot more architectural flexibility in sheen, color, geometry, surface, and so on. You can see the one to that right was a wood or a faux wood. That's become very, very popular. When you think of metal, you think of a very industrial or neo-industrial type finish. Well, with today's technologies, they both paint processes and laminate processes that really give a great facsimile of wood without the upkeep and issues that you'd have with a natural wood. So we can carry these through ceilings, through walls. This is solid panels. On the right side, though, is micro perforated with sound techs. So they can be acoustical units, or they can be simply just, eye-catching, warmth-bringing type units that, once again, we still get all the benefit of recyclability, of second use, second life, and the look of natural woods. Lineal metals, they don't really do this in mineral fiber. This is something that's specific to metals. It used to be very, very popular, 60s, 70s, 80s, 90s to some degree, kind of lost favor. But once again, with the invent of faux wood finishes and wood surfaces, lineal metal has come back as a very, very viable solution, as have metal baffles and beams with the wood look that you see over in the right. So we have that kind of warm, natural feel on the center, a very neo-industrial look on our left, and then a split look beams and baffles on our right, all done with 032 aluminum. The other thing about when we're looking at metals is that the finish options are unlimited. This is just a scratching the surface of different colors. But not only do we work with colors and with different shades in between all of these colors, but we can also work with glosses. We can also make them flat, mattes, manipulate sheen for different effect, embossing, all types of things that we can do with metals that you really can't do with other materials. Not to mention metallic finishes, mill finishes, coateds. We can work with zincs where we grow an anechoic layer. We actually grow crystalline on the surface of the panel itself. It's not a coating, so there's no chance of it delaminating or coming off. Coppers, bronzes, natural metals, zincs, very, very popular, both interior and exterior today. So there's just really, as we delve into metals, or metal panels for interiors, your options are pretty unlimited. With finish options, especially on the wood side, the ones on the lower are looked to be like a distressed, almost a core 10, but all these are PVDF, and PVDF technology basically started in roofing and cladding. Usually most manufacturers are going to give you a 30 or a 35-year warranty. These systems are done by laying down a color coat of PVDF, the lightest coat you see in each of those wood grains, and then a species roller that kind of prints the grains onto that lighter color and makes them darker colors, so you actually get a wood feel. These can be wood grained embossed, so you can actually get a wood texture too. But the thing is, PVDF is literally one molecule off of Teflon. So when you write a user or care and maintenance manual for any PVDF finished metal, if it's exterior, it's going to be 2 cold water rinses. If it's interior, it's going to be 2 dry cloth wipes. So it's virtually maintenance free. And you still get the warmth of either wood. That stack stone is actually a laminate. I haven't seen a lot of call for that, but it is available. Then the other 2 are these distressed looks, that oxidized kind of finishes. And that's done with the same process. We have a lighter color will go underneath, and then they'll roll the distressed piece of it on after the fact. Usually finish it off with a clear coat, face up in the sun, 30, 35-year warranty. We turn that over and bring it inside, and it's going to be a one and done solution that's going to really last the entirety of the building. So wall panels, we can hook them on the walls. We can make entire walls by just creating a girt and keeping the cladding off an inch or two, putting some type of absorber behind that. We've looked at absorbers, a CFAB, a regular fiberglass, spun glass insulation, or Soundtex. Any one of those is acceptable. And literally you can make all of your walls absorptive if need be, if you have that type of volume and want that type of sound control or RT60 calculation under a second or so in your space. These can be modular. Once again, with the modular pieces, we can work with geometry, shapes, colors, texture, giving you all types of flexibility simply by using metals. Baffles, very simply, we can do the same things that you can do with all the fabric wrapped or chemically hardened edge baffles in metal. We're not really following our rule of thumb as far as drop and spacing there on the big picture, but those are also visual elements. And if you notice, the ceiling above it is actually fluted, and there's an acoustical bed above that. So you're catching sound both horizontally and vertically within this learning space. There are systems that are actually modular, change fills, change amount of absorption within by adding blades, subtracting blades. And we can do this over a weekend. So we're not really disturbing the space. We're not disrupting the folks or the flow of the space within it. This is out at HC or H Council Trenholm Technical College in the campus in Morganton. And they had a lot of hard spaces. So they started putting in tricolor and bicolor wall claddings that were micro perforated with a 1-inch sound back behind it, just to kind of bring down some of that noise within it. They did that throughout this building, both in break areas, in like the automotive service centers where they teach people how to work on cars, how to work on diesel, and so on. So they could bring some sound control into these more industrial spaces. But it doesn't have to be industrial spaces. It can be office spaces. It can be waiting rooms, anywhere where you want to reduce some of that reverberation. You can see that lower picture. They've kind of crossed elements of a neo-industrial and a warm wood slatting throughout there. But through micro perforation, Soundtex, all those walls are going to be about a 0.7 or 0.75 absorption. This job's near and dear to my heart. This is in Raleigh, North Carolina. This is the Reynolds Coliseum Hall of Champions on NC State University. And this whole area was built. It was the original Reynolds Coliseum where they played basketball, Jim Valvano in the 50s and 60s. And they built this Coliseum, and it was much smaller. And they built a bigger one, the PNC Arena, which is huge. It's where the Hurricanes play, and they moved NC State basketball over there. They still use this for smaller things, but being built in the 50s, it was just a steam boiler. There was no air conditioning. So they did this big retrofit. They did a mechanical mezzanine, and they stretched out this area to create this Hall of Champions. And what they want to do is honor Hall of Fame athletes and notables, both past and present in this space. So if you look at the end, they put a podium down there. The people would fill the space below it, and they would induct Hall of Fame athletes and do these things. And they went to use it, and it was so echoic. It was 7.2 or 7.5 reverberation, RT60. You couldn't really understand what was being said. The fix was tricolored, factory folded ends, micro perforated, 2-inch sound bats on girts. The panels are on girts. The sound bats are adhered to the wall. They did not get it to a 2.5 second RT60. They got it to about a 3.5, but to a point where you could understand what was being said, where they could utilize the space for its intended purpose. Another place where speech intelligibility can be a safety issue are jails and penitentiaries. This is Wayne County Detention Center. You can see the meeting space there, upper right-hand side by the HVAC squirrel cage. Those are all micro perforated sound panels. Once again, on a 2-inch girt with a 2-inch sound bat. The other side, that long corridor, that's all poured concrete and block wall. So it's a lot of hard surfaces. Above that is actually a security ceiling. So it's a very, very heavy gauge ceiling system, micro perforated. 2-inch sound bat, and they are tamper-proof screws, so you can't get up into that ceiling to hide contraband or try to escape. Or, well, escape would be tough. If someone did get one of those panels down, it's probably about a 3-foot interstitial space and then more concrete. They'd be a little disappointed, but the acoustical benefit helps counteract all those hard surfaces. So if there is a riot, if there is an uprising, if people need to talk, whether it's face-to-face or on the radio, communication can take place much more effectively and much more readily. Pools and caustic environments, whether it's chlorine air or just simple high humidity, metal is going to be your best bet. Perforated metals with PVDF finishes can take on chlorine air, can take on salt air, can take on high humidity without chalking, fading, or deformation. And then we actually it's a very specific fill when we're in a pool or we're in an aquatic center or aquarium or anywhere with high humidity. It's actually the same material that a magic eraser is made out of. It's a kind of a extruded, but it's an open cell extrusion. So it still has about a 0.6 NRC, but it doesn't hold moisture. So it won't mold, it won't grow anything in it because the open cell structure doesn't allow it to. And then of course the aluminum doesn't corrode, fade, chalk, what have you. So the combination of the two, we can get acoustical treatment in areas which are very, very echoic and a lot of hard surfaces, tiles, plasters, concretes. Also industrial and warehouse spaces. We have a lot of processes going on, equipment running. The only thing when we get to these spaces is, generally speaking, if you look at both sides, they're usually framed out. And what that is when you perforate metal, obviously you're taking a piece of it out. So it's losing some of its integrity as we do that. By keeping it perforated in the center only, we're still allowing sound to pass through, but we're giving it more impact resistance. We're leaving the integrity of the metal around the perimeter. So if a cart hits it, if it has some type of impact, a lot is going to be going on that more rough and tumble in an industrial space or a warehouse space than it would be in, let's say, a Class A office space. And this is how we treat those areas. So that's the A of the ABCs. The B is blocking. So we know that perforating, we allow sound to pass through. But if we don't perforate that and we leave it one continuous plane, then by putting some types of ondulation or profile in it, we can actually block or reflect sound energy. So the one on the left here, that's a dentist office there. I believe it's going to be an AR Mason install, but it's a waiting room on one side. They have a wall, and basically the higher frequencies, metal is an excellent reflector and blocker of. Lower frequencies, bass sounds, like I was trying to do earlier, those are usually mass or block, but by combining the two, you get a very wide spectrum of hertz and a really good isolation or speech privacy between the two spaces. The one on the right is Rock Outdoors in Lexington, North Carolina, and their accounting department is upstairs behind that wood decking and then the gray metal cladding. And once again, that cladding is adding a layer of reflectivity because you have basically what is a retail space for fishing boats, camping outdoors, people mulling around there, and then office space on the inside. And we're using that as a blocker. Another part of the blocking could be reflectivity. This is a Shake Shack and a Blaze Pizza. These are both in mall areas. So when we get that deep profile, we have no perforation. That sound is actually going to be parabolically reflected out. So we know nothing really attracts a crowd like a crowd. So by utilizing hard surfaces, not perforating them, we're going to use them as reflectors. We can push sound out into the common spaces. So at lunchtime, as these places start to fill up, the noise becomes louder, the decibel rate goes up, and people are drawn to it saying, hey, look at that. Well, let's go get a Shake Shack. Let's go grab a slice of pizza. And that's the B of blocking, or reflecting of sound with metals. Last but not least is covering. Metal itself doesn't really covering, but we have a lot of systems that we put together, and these systems are usually accessible, especially ceiling systems. So people can get up into that interstitial space and change out lights, work on VAV boxes or HVAC equipment, what have you. But that accessibility also allows for sound masking. Now, sound masking is the introduction of white or pink noise And when I first heard of it, I really thought that, this is a lot of sizzle and a lot of steak. And I wasn't sure about the technology. Independent research shows that the introduction of sound masking, though, not only creates sound privacy, very much like a noise canceling headphone, goes in the same sound wave or mimicking the wave that's coming in or the exterior noise, thus creating that noise canceling. This does the same thing with speech. It creates or introduces a pink noise into that space that is the mirror image of the sound wave of speech. Thus, you can hear people are talking, but you really can't understand what they're saying. When it's turned up, when the volume's turned up, it actually sounds like just static. But it's supposed to be done at a decibel level where you really can't hear it unless you're really concentrating, almost like a light ballast noise, but one that's tuned to reduce speech intelligibility. Where metal comes in is that it's accessible. So we allow both tuning and access into our spaces, whether they're point accessible, push and pull panels, or whether there's some type of access panel like we see up there in the upper right. We create the access and the entry for these sound generators to be placed throughout a space and thus covering noise. And that's the ABCs, absorption, blocking, and covering of acoustics with metal panels. So in conclusion, we know that sound waves create all different volumes, tones, pitches, both audible and inaudible to the human ear. That we can use Wallace Sabine's RT60 calculation to determine the amount or treatment needed in a particular space. That I'm choking on iced tea, excuse me. Sorry about that. That absorptive materials can be placed throughout a space to improve sound performance. And if I can get it out, the takeaway that metal can outperform mineral fiber and traditional materials in strength, resilience, and acoustical performance. And with that, if there are any questions, I would be very happy to take them at this time.
So we don't have any questions currently,
All right, and that's
but
fine. It happens
anyone does
virtually
have-
frequently.
but if anyone does have questions, feel free to type them either into the chat or into the Q&A section while I give my quick little outro. And I hope, we'll see a few before I'm done. So first of all, Kevin, thank you so much for taking the time to be with us today. And for
Thank
doing
you
this
and the
fantastic
Metalcon group and
presentation.
everyone that participated.
Yeah, it was fantastic. And then I also wanted to say thank you to everyone who was viewing today. We appreciate you guys taking the time out of your busy days to attend and get some education with us. As a reminder, AIA credit will be submitted by Metalcon and or ATAS in the very near future. And then we also wanted to remind everyone that if you have young professionals, or if you are a young professional yourself, be sure that you pay close attention to June 22nd's Metalcon Live and register for that when you can. Okay, Kevin, I'm not seeing any questions still, but thank you so much for being here. We appreciate your time again. Thanks, everyone else. Have a great weekend and enjoy the beginning of your summer, guys. Bye.